This is Jim Hendershot again with lecture number 25, which is the next lecture in our series on reluctance synchronous machines. And in this one, we're going to discuss the design aspects of the rotor to achieve saliency that's necessary to get some power density out of this type of machine. The initial assumptions are that we're going to use a stator for the RSM design with our new rotor, with the rotor design we're going to design, that is the same as those used for induction motors. I didn't mention two-pole here. I probably should have mentioned two-pole. I think two-pole reluctance synchronous motors are viable as well. Certainly 4 and 6. I'm not sure about 8-pole, but if 8 poles are considered, you certainly would use the same induction motor stator. It's expected that the rotor to stator air gaps will be identical or similar to induction machines, and they're to be controlled and driven with software modified 3-phase inverters from induction machines. And as we've seen from the last tutorial, through the work done by University of Wisconsin under Tom Lippo, the successful RSM designs are going to have an inductance ratio of 5, 6, 7, or even higher, because the power factor should be at least 0.8 to be successful. And finally, the rotor construction must be more robust than some of those in the past, so that it will withstand the rigors of motoring and be stable at higher RPMs. They continue with the guidelines. The saliency must be optimized, as we keep saying, to maximize the inductance ratio, and it can be laminated axially or radially. And this saliency is produced by flux guides and flux carriers and flux barriers, and we have to maximize this saliency ratio, and the torque and output power proportional to that. And so to compete with the other motor technologies, the ratio has to be 6, 7, 8. And that's a repeat of the last slide, actually. The use of the use of flux carriers and barriers as flux guides to improve saliency and inductance ratio of the circuit. The transverse or radial lamination could make up the rotor soft iron pole sections for high inductance, and alternating or laminating the rotor iron pole sections involves axial lamination punched from the stator bore. Optimizing the number of flux guides and thickness ratio and shaping of the flux guides, and minimize the number of flux carrier support webs, which reduces the inductance. So here's an example of a machine with too big of an air gap, of course, and we see laminated down the length of the shaft, and with alternate layers of the flux barriers and carriers. So our pole is here, that's the direct axis, and in between two poles is the quadrature axis. Shaft can be magnetic or non-magnetic, and we want to achieve a high saliency ratio. We've seen these two pictures before. This is all repetition. Now here's an example of some research work that's been done on trying to determine the number of flux carriers, or flux guides is what this acronym stands for, and they started with 1. Here's one flux guide with not an optimum channel. So here's one flux guide with a channel. Here's a flux guide with no channel. 2 flux guides, 3 flux guides, 5 flux guides. You can see the 2 flux guide channel and the 3 flux guide channels per half a pole, and then here's 5 flux guide patterns, and channels. And what we see from this is the actual values of the measured inductance. I don't know if this is measured or simulated. I think it's simulated from these FEA plots. And so the ratios come out to be very low to medium, still not good enough, but it seems to me that probably a two-pole machine could be, these are all two-pole machines, by the way. It seems like a two-pole machine could be optimized to get a pretty high inductance ratio. You see the flux is, here's the flux trying to go through the direct axis, and here's the flux trying to pass through the quadrature axis, and so I think a two-pole machine is a very good example to use to study this, to build your models up and to model them with FEA analysis to help you see and determine the number of barriers and carriers. There's been a lot of work done on that, but I think there's still more work to be done, because if you look at in the stator poles, stator teeth, not poles, you have a certain number of teeth, and so all the flux from those teeth has to get through the stator. You can't have some of them be blocked by flux barriers. That's not going to give you a very high, and to have the highest inductance in the direct axis, which is what you want, you have to be able to provide carriers in the rotor that will carry all the flux. You don't want to introduce any air in the circuit right at the air gap. So there's work that needs to be done and has been done on determining the number of these flux carriers to carry the flux, and it's going to be different probably from a 24 slot lamb versus a 12 slot lamb, the same diameter, because the tooth widths are different than the air, or the slot openings in the stator are different. So as the rotor rotates, you want to make sure that the maximum number of flux carriers in the air gap of the rotor are passing directly over slot openings, or not slot openings, but tooth widths in the stator. Here's some examples of some more work that's been done. This is the ABB machine. This is the ABB machine. And this professor of electrical engineering at a university in Czechoslovakia has done a lot of work on these machines. She's built laminations that are laminated like this, but these are the ones that she finds the highest inductance ratios on. And by one of the earlier examples, if they're round like this, like Tim Miller's at University of Glasgow, the tooling is different for every one of these carriers. Whereas if you do it like this, you possibly, these are all the same included angle. So it seems to me it would be possible to bend all these in the same die, and so that you'd have the same corner radius in all these, and they would nest together and give, that would increase your saliency, I believe, in the Q axis. And of course, this is non-magnetic here, so here's your alternate pieces of carrier and barrier. I think this yields much higher ratio than this design here. This is a blown up view, so you see the flux is gonna go right through here. There's steel right through there in this because of those until they short out. Now these are going to short out as well. This professor, here's her reference and her graduate students in Czechoslovakia, and you see she's done a lot of work on trying to optimize and calculate the effects of the ratio or the proportions of the barriers and the carriers. But we have some good data coming up on that. Here's the comparison of the radius type versus the B type. I think this type is much easier to manufacture than that type. You'll notice all the radiuses here are, each one has got a different radius, but I don't think that it has to be made that way. I think it can be made, if you make them all the same radius, they're going to nest in each other as well, I believe. You just have a lot of air in here, but you want a lot of air in here, it seems to me. This is a this plot that we showed in the last lecture of the power factor versus the saliency ratio. Here's the saliency ratio here. Here's the power factor. And of course, to get a power factor of 0.8 or higher, we have to have a saliency ratio of 7 or higher. 7 to 10 gives you a power factor of 0.8 to 1. Well, no, not 1. No, 0.8 to a little less than 0.9. So I guess this is a point of diminishing return. I believe that's what this shows us. You're not gaining much by going to the trouble to increase the saliency ratio beyond about this. This looks like the theoretical limit is probably just under 0.9, but it's not a practical limit. This is a practical limit. This is a study that the Czechoslovakia University did on saturation factors versus inverter voltages, which is useful, and those factors have been plotted as a function of voltage. This is a blow-up of a section, which is a introduction to the next sections of this that we want to talk about, that describes the work of the University of Wisconsin. University of Wisconsin has made this sketch showing the tooth width in the stator, and then the width, they call it W, is the width of the iron. Those are the flux carriers in the rotor. And the width of the insulators, those are the flux barriers in the rotor. And of course, there's normally shorting steel across these gaps, but there doesn't have to be, depending on how you make it. So what they've done is an awful lot of work to study this inductance ratio and what effect it has, how it's related, how the inductance ratio is related to the barrier, the flux barrier to the flux carrier ratio. So here's a term that where you divide the barrier thickness by the carrier thickness, but that is the sum of the thickness of the flux barriers and the sum of the thickness of the flux carriers. And the reason you have to sum them up is because you see, this is a carrier as well. The carriers are these. So there's 1, 2, 3, 4, 5 of them in this case. And there's only 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 barriers. So this has to be considered a carrier too. So it's the sum of all these pieces of steel, 2 of those, 2 of those, 2 of those, 1 of those, and 1 of those, 1 of those, or 2 of those, 2 of those, 2 of those. So it's a sum. Now, think about that. If the ratio is 0, that means the rotor's solid. If it's 1, that means the barriers and the carriers are equal thickness. So here's another plot based on the work that they did. Gary Horst, and the professors at graduate students under the direction of Tom Lippo. We've already seen this. That's right. We've already studied this a couple times. This is a saliency ratio plotted as a function of the thickness of. No, we haven't studied this. The thickness of the barrier and carrier. So it would seem that to achieve a inductance ratio or saliency ratio of 10, that's this point here, that the ratio of the carriers to the barriers should be 0.5. That says that the carrier is going to be twice as thick as the barrier. I believe that's what that says. So in doing that, in achieving that, you have to consider that you have to have enough thickness of the carriers to carry all the flux of the barriers. So if you take the number of teeth times this width, then it seems that that total distance per pole has to equal the width of the carriers times the number of them. Otherwise, you're not going to get all this flux in. It doesn't mean they all have to line up at all the time, but it's probably, if they don't line up all the time, then you're going to have some that don't line up. When they don't line up, what I'm trying to say is I don't think that the barriers should line up with the slot openings, because so then you'd have you'd have a ripple effect in the flux distribution as it rotates and tries to pass across the air gap from the stator to the rotor. So, but the main thing is the cross-sectional area, or the width of these, total width of these has to equal the width of the stator teeth. And then you shoot for a ratio. I mean, this is a big step forward. It saves us all a lot of work if we conclude from that that the flux carrier has to be twice as thick as the flux barrier. And there's some other studies that I've seen that show that the number of flux carriers, there's diminishing returns on that to have too many of them. So that's another area you could study. So that concludes this lecture with some guidelines on how to begin to design a rotor and what the proportions of the carriers and the barriers are.